Welcome everybody. Today's webinar is going to be a continuation of our big data series. The focus of our presentation today is really going to be around the data ingestion. More specifically, we're going to focus on two tools that help us with data ingestion, and those are known as Flume as well as Sqoop. Now, we're going to start our webinar by firstly talking about what exactly is data ingestion. We're then going to talk about how Flume and Sqoop help with different data ingestion scenarios. We're then going to delve a little bit deeper into both Flume and Sqoop architecture so you can understand how they operate underneath. And we're going to follow those individually with a couple of demos. Now, typically when you hear about big data and Hadoop, those conversations usually focus around the core components of the Hadoop ecosystem. Things like the processing engines like MapReduce and Spark, the resource management in the form of Yarn, as well as potentially even the distributed storage like HDFS or Tachyon. And there's a valid reason for this, because these are directly responsible for giving you the value that big data promises. But an often overlooked component, but equally important component, is how do you get your data from your different sources into Hadoop so you can start analyzing it with your tools. And that's what data ingestion is all about. It's about having some mechanism and process to get your data into Hadoop for analysis. And there's many ways that data ingestion can be achieved, going from the very basics, such as a copy and paste, through to the very extreme of setting up a complex Kafka environment to stream data into Hadoop from multiple sources. Now, Apache Flume and Apache Sqoop are two well-known and easy-to-use data ingestion tools. Both are open source, and both are designed to tackle different data ingestion scenarios. Now, Flume started its life focusing on ingesting log data into Hadoop. Log data like Apache Access logs or server message logs, of which hold a lot of value, allowing us to do things like web traffic analysis as well as service security analysis. Sqoop, on the other hand, is focused at getting your database data or data warehouse data into Hadoop. From there, you can potentially archive your database data or do analysis on large sets of historical data. Now, talking a bit more about Flume. As mentioned, Flume is designed to move large amounts of log data into Hadoop, and it's designed to be distributed, reliable, as well as available. Going straight into Flume architecture, with every Flume scenario, firstly you need a data producer, next you need a data destination, both of which are external to Flume itself. Firstly, the data producer is the thing creating the data that you want to analyze. In the case of web server logs, that could be something like an Apache web server, or in the case of Twitter feeds, it would be the Twitter API. Data destination, on the other hand, is where you want that data to be stored. In the case of Hadoop, that typically is HDFS or HBase. Now, Flume itself consists of three key components, and those components are the Flume data source, the Flume data channel, and the Flume data sink. And these three components make up what's known as the Flume agent, which itself is a Java process. Starting with the Flume data source, the data source represents the component of the Flume agent that interfaces with the data producer. It acts as an entry point for new data into the Flume agent. Now, there are many Flume data sources. There is, for example, a spooling directory data source. Now, this monitors the directory for new files and channels those files through to the agent as a new event. An HTTP source that listens for new HTTP requests. An average source which listens for average calls. The average itself is an RPC and data serialization framework designed for Hadoop. Exec data source, which monitors standard out from a specific command that you specified, and then sends any new output into the agent as a new event. And last but not least is you can actually write your own custom data source. Now, this is really important because now it means that you can use Flume to ingest data from pretty much any data producer, not just log data, which was what Flume was originally intended for. Now, next you have the data channel. The data channel is a queue or passive storage that holds events, waiting for it to be consumed at the next stage. An event is placed into the data channel by a data source. Now, the data channel really helps Flume achieve that reliable and available aspect of data ingestion. Now, as the channel is really just storage, the channel can be, for example, memory, where events are staged into memory, file, where events are staged in a file, JDBC, where it's backed by the database, and of course, you can write your own custom channels on top of these channels which come out of the box with Flume. Now, lastly, you have a data sink. Now, the data sink pulls events from the data channel and then interfaces with either an external repository to store the data into, or another Flume agent to pass the data to. And again, the data sink is customizable. You can, out of the box, have a data sink for HDFS, HBase, or Hive. And if you are passing to another Flume agent, you would typically use the data sink of Avro, again part of that RTC framework. Now, bringing these components together, Flume works like this. First, the data source listens for new data from the data producer. Next, when data is generated, the data is then passed by the data source into the data channel for temporary reliable storage. Following this, the data sink pulls the data from the channel and then submits it onwards to a repository or another Flume agent. Now, I've mentioned a few times about passing data between agents. By having this source channel sync architecture, we can easily chain agents together. And this means we can create architectures like in the slide, where we could have hundreds, if not thousands of data sources that then funnel down to collectors that have the direct responsibility of writing all that data to the data destination. Now, this architecture really works well if you have massive scale and really helps to reduce management overhead as well as minimize network traffic. Now, similar to this, you can actually use agent chaining to create a multiplex data flow where one event can spread out to multiple data destinations or Flume agents, as you can see in the slide. Now, the final thing I want to mention about Flume is the concept of interceptors. Now, interceptors allow us to modify or drop events in flight, allowing us to put some sort of management around our ingestion process. If, for example, you often have rubbish data you may want to use interceptors to drop that rubbish data instead of storing it. Now, different interceptors exist. A timestamp interceptor allows us to add a timestamp to our header information of the event. Regex allows us to data match and make decisions based on what's in that data. A static interceptor allows us to add static information to the header of an event that we can then process later on and use as guidance or within conditional statements. And naturally, you can create your own custom interceptors. Now, moving on to a demo of Flume. I'm actually going to split this into two quick demos. The first one is just going to show you a very basic Flume configuration, where I show you the source, collector, sync architecture in its most basic form. And secondly, we're going to use a little bit of a more real-world example where we've used that funnel-down chain architecture we saw previously. And we're going to do some Apache access log collection on that second demo. Now, starting with our first demo, I'm going to move over to my demo machine. Now, in this first demo, I want to set up Flume so it's listening on a port. Now, I want to then be able to attach using Telnet to that port where I can submit some very basic messages. And then I want Flume to take those messages and load them into a file in HDFS for analysis. So this is my demo machine here. I've got, it is actually running, it's one of my data nodes in my Hadoop cluster, and I just want to quickly show that I've got Flume installed. Okay, so Flume is installed here. Now I've installed Flume using a Hortonworks repository, but you can actually use Flume directly from the Apache website. Let me flip over to it. So you can use this website, the tar file there, which is exactly the same as I'm going to show you. So back to the demo machine. The binary that I use for Flume is actually known as Flume-ng. Now there's a little bit of a story behind this. NG stands for new generation. There was an OG or old generation, but the Flume Apache team refactored that to make Flume easier to use, and as a result, we've come out with this Flume-ng binary. So any future use of Flume, you will probably use Flume-ng. Now, the directory, the configuration directory for Flume, I'm going to show you here. So for this, when Flume is installed in our repository, it's located at etc flume/conf. And this is my configuration directory here. Now, the configuration files are identified, in this case, by the flume.conf. Now, my configuration file itself defines all the information Flume needs to get started, and that information is going to be the sync, channel, and source configuration. So I'll open that up here, and you'll actually see that this file actually looks a lot like a Java properties file. Now the first thing I want to do when I create a Flume configuration file is give it a name, give my Flume agent a name. And in this case, I've given the name agent to my Flume agent. It's identified by this piece here. And all the way down here it says agent. So I'm going to be referencing my agent as with the name agent. The next thing I want to do is then define the names of the source, the sink, and the channel. And I've defined that here, S1, U1, and C1 respectively. We then want to configure the source. Now as mentioned, my goal is to be able to attach to a port. I want to be able to telnet to that port and type some words in that will then propagate HDFS. And I can do that by having a netcat data source. And this is what I've defined here. My source is using the default out-of-the-box implementation of a data source for netcat, and that allows me to attach to a port. I've got some further configuration here. 0.0.0.0 defines that I can attach to all IPs on my server, and the 444 defines the port that I can telnet to. Next, I want to configure my channel. Now, my channel is a storage area. In this case, I'm using the out-of-box data channel for memory. So I've defined my channel to be a memory data channel. Now, the rest of this configuration gives us a little bit more flexibility. This channel can hold 20,000 events. And the next piece here, transaction capacity, indicates that my source or my sink can either put in or pull out a maximum of 100 events at any one point in time. Now, lastly, I want to configure my sink. My sink is HDFS, and this is what I'm using here. This is the reason why I've defined HDFS there. I've also additionally defined where my HDFS is located, so my name node, and here I define exactly the path where I want that file to exist. This is user data demo 1. The last pieces here define text and data streams define or provide a little bit more information around the data types. Now the last thing I want to do in this configuration file is put those components together. Very simple. The channel for my source, the channel that the source is going to put data into, is the C1 that I've defined in my configuration file, and the channel that my sink is going to pull data out of or events out of is also C1. Again, I've bound those together. Now, going back to the console, it starts the Flume agent. So Flume and G agent defines I'm running this in agent mode. I define the configuration directory for Flume and the configuration file. So Flume and here I define the name of the agent that I want to run. In this case, since I named my agent, I'm going to run that. So let me go ahead and execute that. Give that a little bit of time to load up. And there you go. Now my agent started running. Okay, now I want to now test the agent is working. So I'm going to jump over to my other machine that has access to that same server, and I want to tell it to that appropriate node, or the appropriate port. It's, should I say, the 97-node 4. That is my host, and port 4444. Let's double check that again. A little bit of a technical fault here. Let's take a look at the configuration again. And I suspect the only reason why I've chosen the wrong demo. There you go. Let's go start again. Okay, so let me attempt that again. Hopefully that'll work. It does work. So let me type some information into this. So this is a Flume demo. There's one bit of information I'm going to put in. That's going to put hello to all on the Flume demo. Okay, so there's a little bit of information that I put in. And hopefully that's taken that information, propagated it to HDFS. So let me exit out of telnet. And what I want to do now is check if that information actually has propagated to my HDFS. And there you go. So there's information propagated. Now there's one thing I want you to know. There's a .temp suffix to that file. Now that .temp simply means that file is still open for writing. Now, after a period of time, that is actually going to disappear, and that file is going to be permanently locked. It's going, and then it's going to create a new file for any new information. So let me do an ls again, see if that temp is still there. You can see that the temp has now disappeared. Now, to prove that this is actually coming from Flume, let me actually cache out that file, and it should have the same content as what I just wrote. So, and there you go, the same content. So Flume is indeed working. Okay, so what I want to do now is move over to the second demo I mentioned. So let me clear my screen. Now this demo that I just showed you didn't really have much in the world of real-world application. So the second demo I'm going to run has an architecture very similar to this. So let me show you here. Now this demo, the goal here is to collect Apache log data, and we can then analyze that Apache log data, get a bit of an insight into how our users operate. We're going to just look at the data ingestion piece. We're not going to look at the processing piece though. Now I'm going to use this configuration as I mentioned, and I'm going to do so by chaining two agents together. The first agent in the top left is going to monitor the Apache access log running on the web server, and the second agent is going to take that data, or it's going to be sent that data, and it's then going to store that data into HDFS. Now the two agents are going to communicate using the Apache RPC framework, Avro is beyond the scope of this presentation, but bear in mind that Avro is simply just a framework that helps with the storage and movement of data between two servers, and it was created for the Hadoop ecosystem. So going back to our demo machine, here I've got my web server. It is a basic web server running Apache. It has a very basic website on it. So let me show you the website. This is the website here. So it is running off demoweb.com. Hopefully that connects. It does indeed connect. I refresh a couple of times. It's the same thing. Nothing special there. Now, whenever I refresh or whenever I visit this page, the default action of Apache is to write that access to its access log, and this access log can be found standard default configuration within this directory for CentOS. You can see the access log there. If I tail out the access log, you'll see that it's got some information about the IP address of my visitor, where they visited, in this case the index directory, their browser, as well as the server of the operating system they're running. So there's some useful information potentially for us. Now my web server does also have Flume installed on it. Okay, so let me show you that Flume is indeed installed here. So the Flume packages are installed and the Flume agent will reside on my web server. Now going directly to the configuration. Okay, and I'm going to be running this Flume here, this flume.conf.demo.2. This is my configuration file this time. Now this again looks very similar to the previous demo, but there are some key differences. Firstly, I'm going to be using the exec data source as opposed to previously it was netcat. Now if you recall previously, exec itself takes the command that you specified and then monitors standard out for new output. Here I've defined exec as my data source, and here the command is the command that I specified. In this case, I'm tailing out the access log looking for new entries. And the next thing that I've got here is interceptors. You'll notice that I'm also using interceptors. Now interceptors are really important. Consider a scenario where you've got many web servers funneling down to a collector agent that then submits that data to HDFS. Now, you want to put some management around where that data is coming from or what time it's coming from. So in this case, we're going to use interceptors firstly as timestamp information to every event, so we know when that event's coming in, and we're also going to add an interceptor of host. Host item puts header information into the event about where, on what host did that come from. So this allows us to put a lot of management around how we distribute or place our information on HDFS. Now the rest of it is very familiar. Again, memory for my channel, and in this case I'm using Avro as my data sink. Is defined here, but I'm also specifying the Avro listener, which is on node 4, and the port that is listening on. So let me go ahead and run that. Okay, so that's agent now initiated. Now let's go to the second agent, the collector agent. So this is the configuration of my collector agent. Very similar to in demo 1. The only difference here is going to be the source, which is now listening for Avro calls. Again, my source is set to Avro, another default out-of-the-box data source. It's binding to all ports, and identified by all these zeros, and it's binding to port 4545. Again, HDFS is my sink. Very similar to previously. I've got a little bit more configuration here. My channel is memory, and I'm also binding these together. So let me go run this agent. Okay, so this agent's still running. Give it a little bit of time to execute, and that's now run successfully. So what I want to do now is, what we intend for this to happen is every single time my website is hit, it's going to update the access log. The Flume agent is then going to recognize that change, is then going to propagate that change to my collector agent, which is then going to write those changes or those access log entries into HDFS. So if I refresh a few times, that should then update the access log. Now hopefully that process is followed through, and let's see if those updates have propagated to HDFS. So HDFS, DFS, data 2. Okay, and you can see here that this information has indeed been propagated across the .10. Again, means that the file is still open for writing. So we'll give that a little bit of time to close that file, otherwise we won't be able to read the file. But I will start up. Get this ready so we can identify the file. Okay, and there you can see the access log entries have actually been propagated to HDFS, and we can actually start performing some analysis on that. And bear in mind that this is all live. This is streaming the information in, as it were. So moving back to our presentation, and onto Sqoop. So, as mentioned, Sqoop's function is to bulk move data in our databases into and out of our Hadoop cluster. Now, out of the box, Sqoop supports multiple databases. You've got your relational databases like MySQL and SQL Server, documents stored in those SQL databases like Rackspace, as well as your data warehouses like Netezza, as well as Oracle. Now, Sqoop is just a client tool and not a daemon process like Flume. It brokers the movement of data between your Hadoop environment and your database environment. And just like Flume, it can import data into things like HDFS as well as HBase. But additionally, it can also support or export data back from Hadoop into your databases. Now, Sqoop consists of two pluggable components in addition to its base libraries. These are the connector and the driver. And these are both used to connect to the database. Now, the connector's goal is to fetch metadata about the data being transferred in flight. Details like the column name and the data type. And really, doing this allows us to ensure data transfer is as efficient as possible. There are different connectors customized to different databases and optimized for communication to take advantage of the different features of each database. And there is also a generic connector to allow us to access databases without customized connectors. The driver, on the other hand, refers to the JDBC driver that provides the JDBC Java API for a database. Now, typically, the connector defines which driver to use. For example, the MySQL connector defines the MySQL connector J driver. But you can specify your own at the command line. Now, bear in mind that many database vendors do have to write their own JDBC driver, and they can be proprietary. So for some databases like SQL Server and Oracle, you may need to download these separately and license them separately before you can properly use Sqoop. So Sqoop works like this. The client initiates the Sqoop tool, and the connector that you define will be based on the database that you use. The connector or you will then specify the appropriate driver, and then a connection is established between Sqoop and your database. Now, once that connection is established, Sqoop initiates a MapReduce map operation to move data between the two environments. And data is typically imported and exported into and out of Hadoop in CSV format. Now, moving on to the demo, in the interest of time, I'm really just going to do a quick demo showing the import operation that Sqoop can do. Now, I do have a database up and ready to go, and database is here. If I connect to it, you can see that there's some databases running in it. I'm going to be using a database classic model, so use classic models. And you can see that it has some tables, some very general tables in it. And to show you that there is some information in those, select staff and customers table. Select staff. And you can see that there is some information with customer details in it. So going out of that, let's go back to our Hadoop machine. We'll close off these Flume agents, clear the screen. Now, Sqoop is just a client tool, as mentioned before. You've got Sqoop, and I'm going to be running an import operation here. That import operation will basically tell you the mode that Sqoop is going to be in. That import operation, my next step is to connect to my database. I define the database I want to connect to. Now, JDBC MySQL. Now, this piece is really important because this piece defines the connector that I'm going to be using. I then define the database the database host name, so demodb.csrex.com, and the database itself that I'm running, classic models. Username for my database, demo1, password. Okay, and the table I want to import, in this case customers, and the target directory, which is where in HDFS am I going to be storing this. In this case, I'm going to be storing in this directory here. Okay, this is going to take this in, copy this. Okay, so let's run that command. Okay, so Sqoop has now set that job up. It's connected to MySQL, as you can see here, and now it's running the MapReduce map operation that I mentioned before, and that's going to immediately bring that data in. So now it's actually brought that data in. Now let's actually go ahead and look at that data within HDFS, and we'll see how it's imported it in the CSV format. So firstly, let's identify that it's actually there. Customers. And there you go, we had a successful operation, and it's output some information. Let's go and look at the first part, and we're going to cap this out. Now what this should be is a CSV file with all my database information in it. And there you go, you've got the database information in it, spread across those 4 files. From there we can then do some analysis for archiving of that data. So back to the presentation, really this brings us to a close. I do really hope that this webinar about data ingestion has been useful so that you can start putting the pieces of Hadoop together for your project. I would like to thank you for attending, and I do hope to see you next time. Thank you very much.